Thank you. I'm Kenyon from Los Alamos. I hope there's still some food and alcohol left by the time we're done with these talks. I'm going to talk about sparse scaling approaches to sparse coding approaches to a multi-INT processor. And I'm a little ahead already, I guess. Okay, so sparse coding is actually very easy to understand if you're not familiar with sparse coding. All sparse coding is a technique for learning a basis that is optimal for representing a given data stream. So in this example, the data stream is a set of, just a set of photographs, and this is supposed to be a movie. There it goes. I think the movie's actually starting finally. So the idea is that the basis elements we learn are optimal in the sense that they allow us to reconstruct each input with great accuracy, but using as few basis elements as possible for each input. And you can see the dynamical process that we use to construct a sparse representation of each input on the bottom right. And you can see that starting with random features, we're able to self-organize in response to essentially any data stream, a basis that is optimal for representing that stream. So it stands to reason that if one level of sparse coding is good, two levels must be better. And indeed, we see that's the case. So if we learn a sparse representation on top of a sparse representation, in fact, we find features that are bigger. They explain more of the visual space. They're more complex, generally, they're individually more complex, and there are more of them. So we can use this more diverse representation that we obtain at the second level to train a classifier for something like, say, target detection. And so you can see in this example that our classifier was very confident that this image contained a target that was a cat. And in the next image, you see the classifier was almost as confident that this image contained a train. Now, you say, well, we could have gamed this, and we didn't. These are actually test images we didn't train on. But come to the Los Alamos booth. Come armed with your images. This is a challenge. We will send it up to the cloud. We will run our classifier on your images, and we'll see how well we do. So that's the challenge I'm issuing. Now, so we can learn sparse codes on different data sets. This is an example of a sparse code that we've learned on global IR weather data. In this case, the features we learn are dynamic. They're not static. They evolve in time, and they tend to capture some of the local dynamics of weather systems. You can see our reconstructed weather on the bottom. It does capture some of the essential dynamical properties of weather. So that's one example of sparse coding applied to a different data set. This is a second example of sparse coding. In this case, we're coding commodity futures prices. Why are we doing that? Well, one, the data is available for free, but also we thought, well, this is a good way to test our multi-INT ideas, that if perhaps there's some crazy correlations between weather and commodity prices, and if our multi-INT processor is worth the effort, then perhaps we can discover these high-level correlations. So let's put it all together. So to put it all together, we're actually inspired by some very influential models of the cerebellum. The cerebellum turns out to have a similar multi-INT problem to the one that people at this conference are confronting. So here's how our proposed multi-INT processor will work. First, we take each data stream and we make a sparse code of each independent multi-INT stream. So each stream is being represented with a sparse representation. We then take those sparse representations and we scramble them. We throw them down randomly on a stack of 2D grids. We then learn a second level of sparse coding on top of those randomly distributed individual data streams. The idea is the random distribution allows us multiple opportunities to find high-level correlations among these different multi-INT streams. And then given this second level of sparse representation, we think we can do the sort of classification and anomaly detection, some examples of which I showed you with the still images. So I wish I had more time, but if you come to the Los Alamos booth, you can talk. We'll have plenty of time to talk there. I'll just summarize. At Los Alamos, we have capabilities for learning sparse representations of different data sets. These data sets can be unlabeled. They don't require any extensive human annotation. We have ideas for how these diverse data sets, these diverse sparse representations can be combined following ideas that were originally developed in the context of the cerebellum and used to detect threatening situations or anomalies. And finally, all of the results I've shown you were generated on linked GPU instances in the Amazon cloud. So everything we do is very neuromorphic and inherently scalable. So thank you very much.